Hey, good afternoon, everybody. Hope everybody's doing great today. Today we're going to talk about hydrostatic forces on plane surfaces. So let's get started. Okay. All right, so we're at lecture 8. I'm going to cover a number of main points today. Hope everyone can see the slide that says today at the top, and then under that it says hydrostatic forces on a plane surface, section 2.8. We're going to figure out how to calculate the resultant force on a surface that's submerged in a liquid. We're going to learn that it acts at not the centroid of the area of the surface, but at a different location called the center of pressure. Very important, because this is probably the #1 place where people make mistakes when they're learning this. They apply the force at the centroid. The centroid's important in these problems, but that's not where the force acts. And then how to calculate where the force does act using the good old parallel axis theorem that you learned in statics. And then we'll just see how these ideas apply to an underwater gate. First, we're going to do something a little bit different today, mix it up. Instead of doing a think, pair, share, we're going to watch a video on the Hoover Dam. So if you haven't heard of it, it's a pretty fantastic dam. When it was built in the 30s, it was, really lauded as an engineering marvel. And I'm going to ask you to watch this video and see if you can collect enough information so that when you go into your small groups of 4 or 5, you'll be able to calculate the pressure behind the dam in that headwater at the very bottom. Okay, so everyone's got that? You're gonna watch this video, try to collect enough information so that when you go into your small groups, you'll be able to quickly calculate the pressure down here behind the Hoover Dam. Yeah, we got a little ad.
Did you know Geico is now on?
Can everyone see the YouTube video that came up that now has an ad?
Yes.
Thank you. So soft. Save an extra 15% when you switch by October 7. When completed in 1935, Hoover Dam was called...
All right, just want to full screen this, but my cursor has disappeared.
When completed in 1935, Hoover Dam was called the 8th wonder of the world. Rising 221 meters, it contains 6 million tons of concrete, enough to pave a road from New York to Los Angeles. A gigantic concrete pyramid, wedged in a desolate canyon, straddling the Nevada-Arizona border, 56 kilometers from Las Vegas. The reservoir created by Hoover Dam, Lake Mead, covers 620 square kilometers and has a storage capacity of over 35 trillion liters, enough to cover the entire state of New York in 30 centimeters of water. Hoover's hydroelectric power plant has 17 generators capable of producing 2 million kilowatts of electricity, enough for 1.7 million homes. In sum, a gargantuan public works enterprise.
I think it's one of the examples of an engineering project where a group of people came together and achieved a very advanced goal as far as the quality of thinking through engineering from beginning to end.
Now, What if Hoover Dam were built today? What changes would engineers make? And what would they do the same? Would the dam have the same design? Could the reservoir store more water? Could the power plant make more electricity? And what about the environment above and below the dam?
They really didn't have a sense in the 1930s of ecology and what kind of damage might be done that they couldn't even imagine. They've only begun to realize that in later years.
There's this ridge here and this ridge here that are huge natural abutments.
We asked an elite team of engineers, hydrologists, biologists, and dam construction experts to consider these questions and tell us how they would reinvent Hoover Dam. To begin this complex reinvention, one must first imagine the location before Hoover Dam was built.
All right, so we'll stop there. So hopefully you feel like you have enough information now that if you had to, which you do need to, you can go ahead and estimate the pressure at the very bottom of Lake Mead behind Hoover Dam. So we're going to go ahead and go into small groups of 4 or 5. You're only going to have about 5 minutes, so go ahead and introduce yourselves if you don't know each other, and then hopefully you'll be able to pair a piece of information you heard in the video with some constants that you can find in the tables from chapter 1 in your textbook, maybe table 1.6, and estimate the, I don't want an exact number, but just an estimate of the pressure at the very bottom of Lake Mead, right behind the Hoover Dam. So here we go. Go ahead and join your breakout rooms. And we'll come back and we'll have a poll and vote on the estimates.
I didn't get an invitation. I think my internet cut out.
Oh, okay, hold on.
Thank you.
Matthew?
Justin?
Justin. Let's see. Okay, got it. I'll put you in room 6. There you go. Did you get an invitation?
Sorry.
No problem. Okay. Did you get an invitation?
No, I did not.
Oh no, what's going on? All right. There you are in room 6. It says not joined. So it looks like on my end that I might be sending you invitations, but you have maybe pop-ups blocked or something. Do you think that's possible?
I don't think so. Let me see. No, I don't.
No.
Just close out of everything in the background.
All right. So let's go through it together. Hi, okay. I'm Ann Staples.
I'm Justin. Nice to meet you.
Nice to meet
or
you.
Nice.
Nice to sort of meet you one-on-one.
Yes.
Right?
Yeah.
So how are you liking the class so far? What are some of your good things and not so good things?
I don't know if I have not so good things, but I like it a lot. I think it's really a lot more interesting than like just regular dynamics, which I found interesting, but I'm excited to like learn more of how like complicated fluids can be. I've enjoyed learning and like reading the textbook.
Awesome.
No, I've always loved water. I know that's weird, but I like swimming, and I think it's interesting to learn about its motion.
Yeah, for sure. And when you think about how much, in the universe, or at least on Earth, is liquid or fluid, gas, right?
Mm-hmm.
Cool. Well, it's nice to hear that. Yeah, I always try and sort of tie the topics we're learning to something that people can really wrap their intuition around too. So I don't know,
Right.
with online learning, I feel like you can't just jump right into the the dry lecture material.
Yeah, it's hard.
So we've only got a couple minutes. I've been gabbing. We've got a couple minutes left. So do you have a sense for how to estimate the water pressure at the bottom of the lake behind the Hoover Dam? Or did you miss the video?
Yeah, my internet cut out.
Okay.
But if um
So we watched a video and you didn't see it, but it basically showed you a little bit about the Hoover Dam, how it was this engineering marvel in the 30s when it was constructed.
right.
And it makes the artificial lake, Lake Mead, part of the Colorado River system. It's 220 meters high.
Wow.
And we know that the water behind it is still, so we can use our equation of hydrostatics to estimate the pressure at the bottom of the lake.
Okay.
So we would say at the top surface where it meets the air, its atmospheric pressure will set that equal to 0. And then the pressure at the bottom is just the depth times the specific weight.
Okay.
And then we can find the specific weight of water in table 1.6. So gamma for water is 9.8 kilonewtons per meter cubed.
Right.
Times 220 meters. Oh my goodness. All right, I better jump back out and all these rooms here. Let me give everybody 1 minute warning. Okay. So basically we're taking the 9.8 kilonewtons per meters cubed and just multiplying it by the 220 meters. And I'll do a little poll in a second once everybody's back.
Okay, thank you so much.
Again. Yeah. But you can sort of apply this idea that we've learned in all sorts of situations.
Yeah.
Sorry, I wasn't able to add you to a breakout room. Not sure why.
No worries.
Okay. All right, everyone, as you're coming back, I hope that you were able to meet some new people and sort of get to the bottom of how to do this estimate of the pressure at the bottom of Lake Mead behind the Hoover Dam. And so for me, this is a good sort of temperature taking exercise to see, is this concept sort of at your fingertips already? Or are we too early? Sort of where is everybody? Are we all on the same page? All right, so it looks like everybody's back now. So the piece of information that I was hoping that everyone would grab from the video was the height of the Hoover Dam. And so in the video at the very beginning, they said it was about 220 meters high, right? We can assume that the lake behind the dam is basically still and not moving. So we're dealing with hydrostatics. And then we can use our hydrostatic equation that the pressure at the bottom of the lake should be equal to gamma of water times that height. So let's see how everybody did with their estimates. Let's see what you came up with for your estimate. Here we go. All right, results are coming in. Pretty good spread with the correct answer leading, so that makes me happy. Just wait until we've got a few more answers in. All right, and it doesn't look like our answers are climbing anymore, so I'm going to go ahead and end the poll and share the results. And here we go. I'm very happy to say that the leading result, 2000 kilopascals, is the correct one. So what you need to do is take our equation for hydrostatic pressure. The pressure at a depth is equal to pressure at the top if it's open to the atmosphere, plus the depth h times the specific weight of the fluid. So in this case, water. So if we look in table 1.6, we see that the specific weight of water is 9.8 kilonewtons per meters cubed. We multiply that by the 220 meter height of the Hoover Dam that we heard at the beginning of the video, and we get about 2000 kilopascals. All right. So let's go ahead and go right back into the slides. All right. So about 2000 kilopascals down at the bottom of Lake Mead behind Hoover Dam. Okay, and of course, this is the same principle that's at play if you're thinking about the physics behind escaping a sinking car. If you got a chance to look at this week's discussion question, I asked you to watch a video about how to escape a sinking car and to answer why in that video do experts say not to try to open your door, to open your window instead, right? So the reason for that is that inside your car, if your windows are closed, the air will be at atmospheric pressure. But because you're at a depth in water, under the surface of the water, you're going to be at greater than atmospheric pressure over your door. And so generally speaking, that pressure difference is too large to overcome, makes too large of a force. And this picture is from problem 278 in the textbook, and Hyung-gun is actually going to be solving this problem on Friday in the problem solving session. All right, I'm going to switch over to the annotator now. Just one moment. All right, so hopefully everyone can see the slides I'm sharing from Annotator. It's the title slide on the lecture notes here. So I want to talk about this picture you're seeing in front of you. It's figure 216 from the textbook. And what you're looking at is a tank just filled with a liquid. That liquid has a specific weight of gamma. Okay. The top of the tank is open. So it's open to the atmosphere. So we know that we have atmospheric pressure there. And in fact, that's what that little upside down triangle indicates. In all these sketches in fluid mechanics, it means open to the atmosphere, so you can assume atmospheric pressure there. Or if we just care about gauge pressure, which is usually the case and not absolute pressure, then we say that the pressure there is 0. Okay. So the tank, the water in the tank has some depth h. And if we're looking at on the left here, what is the resultant force on the bottom surface of the tank? That's easy. It's the same everywhere. It's the same gamma times h everywhere across the bottom. So you can just integrate across that area to get the total resultant force F sub r. Okay. However, when we ask the question, what is the pressure force on the walls of the container, it's a little bit more complicated because pressure increases linearly with depth. We see that the pressure force gets larger and larger in magnitude as we descend. So it's not just a simple rectangular distribution like it is for the floor, because we have different heights here. So what we have to do in this case is integrate the total sum, the total contribution of all the infinitesimal pressure forces DFR at each location. All right, so now we're moving over to the case of an arbitrarily shaped planar surface that's submerged underwater. So let's just walk through this figure for a moment. This is 217 from the textbook. We've got this pink shaded region, which is the fluid. We'll assume it's water. We've got that upside down triangle at the top. That means that it's open to the atmosphere. We've got a free surface. We've got a depth coordinate h that tells us what the vertical distance is from the free surface. And then we've got another coordinate y that goes along the surface of the submerged plane. So here we're looking at it from the side. Here we're turning it 90 degrees. So we're looking at this arbitrary shaped area, this arbitrarily shaped surface face on, right? So this surface is at an angle theta with respect to the horizontal. And you can imagine considering the differential force dF at any point on the surface. We can look at it at a point x, y. Okay. The resultant force, the total, acts here, and it's denoted by capital F sub r. Okay, a couple other things to notice on this rotated view of the submerged surface is that we've got two places noted. We've got C, which is actually the centroid of the area, but then below that we've got CP, which is the center of pressure, right? And so because this shape is experiencing a non-symmetric pressure distribution, the center of pressure is not at the same location as the centroid. All right, well, there's a bunch that we can do here. For any depth h, the force acting on a little infinitesimal area, dA, shaded in red here in the figure, is dF. And it's just equal to gamma h dA, right? So whatever the height of your little dA is, it's the pressure at that height or at that depth. So the resultant force is just the integral of all these little forces, dF. So we integrate over the entire area, gamma h dA, which is also equal to gamma y sine theta dA. And that's because if you look at over here on the figure, we've got this triangle here, theta, the long side, the hypotenuse is y, and then h, so you can see from the triangle that h is y sine theta, right? So that's the geometric information we're using over here in our formula. Now, most of the time, we can assume that gamma, that it's the same fluid and it's not undergoing, massive heating or something that would cause gamma to change. So for gamma and theta constant, we can say that the resultant force is gamma sine theta, and then it's just the integral over y dA. And that's equation 217 from the textbook. This is the first moment of the area, this integral. With respect to the x-axis. So we can write it as the integral of the area of y dA is equal to yCA. Now what's yC? That's the y coordinate of the centroid. Okay, so if you look over here on the figure and you trace down the y-axis, we see yC here, we follow it over, we see that it's the y location of the centroid of the shape. Okay, so we can write this as the resultant force is equal to gamma A yC sine theta, or the resultant force is equal to gamma HCA. Okay. And this puts it in pretty simple terms. Okay, so what is this equation here saying, 218? It's saying that the resultant force from the pressure distribution on the entire surface that's submerged is the pressure at the centroid times the area of the submerged surface. Okay, so the centroid is important in calculating the force on a submerged object. It's just not where the force acts. Okay, I'm going to keep driving that point home because it's such a common place to make an error. All right, so if we want to calculate the resultant force on a submerged planar surface, we find out at what depth the centroid of the area is located, use that depth to calculate the pressure by multiplying it by gamma of the fluid, and then multiply by the entire surface area of the submerged surface. Okay, it's equation 218. Oops. Okay. All right. So if we look at this really simplified version of the figure that we just looked at, hold on, I've just got somebody to confirm the C in equation 218 is a subscript. Yes, it is. It's y subscript C, and it means the y location of the centroid. Thanks for the question. So here we've got a really simplified version of the complicated figure we saw on the last page. I just want to make a few points. So we've got some fluid with specific weight of gamma, and then we've got the location of the centroid, the depth of the centroid, so the vertical location of the centroid. And we've got our resultant force, which we know now is equal to gamma H sub C times A. And this is our submerged surface with area A. Well, here's the centroid C, and then down here where the force acts, that's CP, the center of pressure. They're not co-located, right? So very, very important point. Just a quick question in the chat. So on the last equation on the previous slide, we don't need to use the angle. That's right. You do need to sometimes use the angle to just figure out what the vertical depth of the centroid is. You may need to use the angle. But to calculate the magnitude of the resultant force, you just need to know the vertical depth of the centroid, the gamma of the water, and the surface area of the surface. That's right. All right. How come? Okay, so how do we find out then where this resultant force does act? It doesn't act at the centroid, which is what our intuition might have told us because we took statics, right? A lot of times in statics, we just had a uniform distribution of a force when we had distributed forces, and that force would act at the centroid of the shape. Here we have a non-uniform distribution, a linearly increasing one with depth, right? So we need to find out where the center of pressure is located, and we can do that by summing the moments about 0 here. So this is the same figure that we looked at 2 slides ago. And now we want to figure out how to find out where that center of pressure is located. All right, so we're going to sum the moments around 0. And that gives us, if we go down here to the result, we look at the resultant force, our moment arm is y sub r, right? So we've got F sub r times y sub r that's giving us a positive counterclockwise moment. But that has to be, because we're assuming that this surface is not moving, that everything's static, that has to be exactly balanced by the moment of the distributed pressure force, y df. Or we can write that as gamma sine theta y squared dA. So we've got the moment of the resultant force, and that has to be the same as the moment of the distributed pressure force. So we note that we can rewrite F sub r like this: gamma a y c sine theta, like we did 2 slides ago. Then we can take these equations in the top line here and just rearrange them, just dividing by F sub r on the left on both sides. Then we write it like this: over. So this, in the numerator, we now have the moment of inertia around the x-axis. So we can rewrite this as Ix over YCA. And we can now use the parallel axis theorem to write this in terms of the moment of inertia with respect to an axis that passes through, an x-axis that passes through the centroid of the shape, right? Because that's a little simpler. Whenever we have a lookup table, oh my gosh, what's the centroid of a triangle? What's the centroid of a rectangle? You know, et cetera. It's given in terms of, it's often given in terms of the moment of inertia with respect to an axis passing through the centroid, right? So using the parallel axis theorem, which tells us that the moment of inertia with respect to the x-axis is equal to the moment of inertia with respect to an x-axis passing through the centroid plus the area times the vertical distance squared, right? So we can do that and we get the following expressions for the y coordinate and x coordinate of the center of pressure, which is where the resultant force acts. So we've got IXC over YCA plus YC. Super important formula. You'll be using this a lot. That's 219. And similarly, I'll just write it right next to it. We can do a moment balance about the y-axis to find the result of the x coordinate, find the location of the x coordinate. All right, just one note here. You'll see that in my formula 219 here for the y coordinate, we've got just IXC. But over here in the formula for the x coordinate, where the center of pressure is located, right, we're finding the coordinates of this point here, where the resultant force is acting. We've got IXYC, and that's the so-called product of inertia, if you remember from statics. And usually if you look at your table from your statics textbook or wherever it is that you look up of a moment of inertia, in addition to the regular old moment of inertia, let's say for a rectangle, you'll be given the moment of inertia about an x-axis at the bottom edge of the shape. You'll be given a formula for the moment of inertia that passes through the centroid, and then you'll also be given the moment of inertia, this product of inertia. But let me just make a little note here. All right, we're actually doing really well on time today, amazingly. So a couple of notes. The XYC, yes, is all subscript. So I'm sorry if my writing is not super clear. You can always, so the equation numbers I'm putting, those are the same equation numbers. I make sure they're the same as the textbook. I don't renumber them so that you'll just be able to cross-reference back and forth with the textbook. All right, now we've got this figure again. We've got a really simplified version of that figure, that complicated figure we're just looking at. And this time, instead of having H sub C denoted on the figure, right, now we've got Y sub C denoted on the figure. YC, Y sub C is the Y location of the centroid, not the center of pressure. So it's different from Y sub R, right? Y sub C, Y location of the centroid. Y sub R, Y location of the center of pressure, or Y location of the resultant force. And so I guess what I just want to drive home here is we've got a resultant force acting right here at the center of pressure, and we've got C, and we can see that they're not co-located like we talked about last time, but also that the distance between C and CP is precisely the moment of inertia of the area over the Y location. And then just an interesting note, we see here that the center of pressure is above the centroid is above the center of pressure. That's always true in these hydrostatic situations, right? Because we always, let's say we have a vertical surface, like we saw with that tank in the very beginning, we're always going to have a pressure distribution that looks like this. The magnitude linearly increases with depth, right? So it's always going to be the case that the resultant force acts at a location that's below the centroid of the area. Okay. But interestingly, the deeper and deeper the object is submerged, the closer those 2 points come together, and we can see why. Since the location of the centroid is equal to this, C and CP get closer together. And I'll just say C gate example, because I think that illustrates it really nicely. Great. So here we have, this is figure, I didn't write it down. Let me take a look here. I want to say 219 from the textbook, but don't quote me on that yet. 218. So here we got figure 218 from the textbook, and it just gives you the geometric properties of some common shapes. So we've got rectangle, semicircle, triangle, circle, quarter circle. And you can see here, it's listing, like we'll look at the rectangle, it's listing the moment of inertia through the centroid. Actually, it's only in this particular table. In the statics textbook, you get a little more, but in this particular table in your fluids textbook, you only get a listing of the moment of inertia through the centroid. So we really need the parallel axis theorem to be able to compute y sub r and x sub r, right? So here we've got the centroid of our shape right in the middle. We've got the formula for the area of the shape. And then we've got our formula for the moment of inertia about an x-axis passing through the centroid, y-axis, and then we've got that other quantity that we talked about, the product of inertia here, right, x, y, z. Usually in this case, for the examples you'll be looking at, you're going to be dealing with something rectangular. There are lots of marine examples used when you learn hydrostatics, you know, about gates underwater, right? And how much you need to, you know, where you need to put a force to get a gate to open, that type of thing. Do we have any questions so far? All right. All right, so let's just sort of look at these ideas applied to an underwater gate. So if you look at the figure on the left here, you can see that on the left side of the gate, you've got water, but it's not to a very high height. So this is something like a dam, right? And on the right side, you've got water also, but it's at a much higher height. Both water reservoirs are open to the atmosphere on top. So we know the pressure, the gauge pressure is 0 there because that little upside down triangle. And then we've got a gate and it starts, presumably the hinge is right here at the water level on the left. We've got the centroid of this gate shape. So it looks like it's probably rectangular. And we've got the resultant force on the left, and we've got the resultant force on the right here. So we can sum moments around, let's call this point 01. Let's call this point 02. We've got depths H1 and H2. Some moments around, let's say 01. And let's say that counterclockwise moment is positive. So we've got our resultant force on the left times the y location of that resultant force on the left must be, if there are no other forces acting on it and nothing's moving, must be equal to the resultant force on the right times the location where that resultant force acts on the right. Right, we're assuming there's no sort of latch or any other way to apply force that's keeping the gate shut. So we can rearrange this. For example, solving for the resultant force on the right, just the resultant force on the left times the ratio of the two vertical distances where they act, right? So you can see, for example, if the force acts on the left, 3 times y right, which is actually not matching with this figure, then you have FR right is equal to 3 times FR left. Right, that actually does not a good match because that assumes that water's higher in the other way. But I want to, but you can put, you know, whatever, you can imagine whatever differential heights that you want here. Right, so we'll be doing this a lot for the example problems and the homework problems for this particular section, hydrostatic forces on planar surfaces. Next, we're going to look at hydrostatic forces on curved surfaces, but that's after the exam, exam 1. I want to point out one last thing, and that's just this. So we'll say that CPR is equal to CP right. CPL is equal to center of pressure on the left. And just notice that the place where the resultant force acts on the right is much closer to the centroid than it is on the left, right? So that goes back to what we talked about 2 slides ago. The deeper a surface is submerged, the closer the center of pressure and the centroid get to each other, right? So you can see over on the right here, we've got a large column of water. So on the right, that gate is submerged to a much deeper depth than it is on the left. So that's why you see the center of pressure on the right and the centroid are much closer together than they are on the left. All right. So that's it for today. I can't believe it. We are ending on time today, but I just wanted to give you a few reminders. Problem solving session with Yangan on Friday. He's going over these problems from the textbook. In particular, problem 278 is that sinking car problem, underwater car problem, and whatever questions you have about the homework or anything else, bring them. Your buddy groups are going to be finalized this week, finally, and made visible so you can start communicating with each other. And just a reminder, exam 1 is in a week already. So what that's going to look like is it'll be available for a 24-hour period. So from midnight on, you know, Wednesday morning to midnight Wednesday evening, it'll be available. You can take it whenever you want. You'll have 50 minutes to take it. But I will be available in real time during class time. There is no class on Wednesday in a week. We're not having a separate class. That's just because I know everyone's available at this time. I'm going to make myself available then to answer any questions you have about the exam. So if you want to take it during class time, that might be a good time to take it. It covers all the material through today. So from the very basics of fluid dynamics, some fluid properties that we learned a little bit about, like, you know, surface tension, Newtonian fluids, up through hydrostatic forces on submerged planar surfaces. So with that, I'll ask if there are any questions about the material we covered today. What will the question format look like? It's going to be a mix of, you know, multiple choice, true, false, and actual problems that you have to work out and solve numerically. Any other questions? Is that on a lockdown browser? I haven't decided yet. I haven't used the lockdown browser before. I am going to, you know, allow a formula sheet, but ask you to have closed, you know, textbook and internet. So I haven't made a decision about lockdown browser. If anybody has thoughts or feelings about lockdown browser and they'd like to share them, please, I'm completely open. This is the first time I'm doing an online in real-time exam like this. So please just feel really free to share your thoughts. Anything else for today? Yeah, I've never used it before either. All right, well, here we are at 2:15, actually on time today. Thank you everybody for showing up today and learning some fluid mechanics. Oh, lockdown browser crashes a lot, that's good to know. Okay. And have a good weekend. Be sure to go to Hyungan's session on Friday, and I will see you on Monday.